Okay, today we are discussing something strange and important because the power of condensed matter, solid state physics, is that some things that don't exist can exist. Okay? And one of those things is low-dimensional worlds, and today we're going to talk about some of the unique things that can only be observed in 2D, 2 dimensions. When I was a bit younger, I read this book. You know this book? Anybody read this book? Do you remember this picture? So Stephen Hawking was conceptualizing that, you know, if our world were to be 2-dimensional, there are some specifics that come with that. And so, for example, a 2-dimensional animal, if it were the same as a 3-dimensional animal, would not exist because it would fall apart. There'll be 2 parts that are, there's nothing to connect them. So, something like this. But except when I was reading this book, I was a teenager, and it was just a purely conceptual idea. We do have 2-dimensional systems and even 1-dimensional or even 0-dimensional systems now in condensed matter. And so we begin with 2-dimensional systems today. We're going to go on to 1D and 0D next time. Okay, you actually already know one example, right? Graphene is a 2-dimensional system, and it also gives you a feeling for what we mean when we say 2-dimensional, because of course we live in a 3-dimensional world. The laws of 3-dimensional world apply, Newton's laws and so on. But in the world of quantum mechanics, in solid state physics, we have structures like graphene, which are single layers of atoms, and they are 2-dimensional in the following sense, that the wave function of an electron in graphene is so tightly confined in the 3rd dimension, so perpendicular to the graphene plane, that the wave function takes the entire sheet of graphene, right? In fact, in graphene, it's to the extreme, because you remember we had those free electrons, and they are due to the 4th unhybridized orbital, right? It's a p orbital that sticks out of the graphene plane like this on each side, and those orbitals are the entire wave function, and then tunneling, hopping from one of those orbitals to the next is what gives us this unique band structure of graphene. And in this band structure, we have only 2 dimensions in our dispersion relation, right? We have kx and ky. Kx and ky. We don't have kz. And in this sense, it's 2-dimensional. In practice, we do have kz in a sense, but kz is given by the size of this orbital. And you can imagine quasi-classically that there is a point particle that travels up and down along this orbital, hops from the bottom lobe to the top lobe, and does it forever. And the velocity of that particle is the kz, right? But it can only have one single value given by the nature of this wave function. So the true reality is not this semi-classical picture. The true reality is that there is a quenched dimension in this system. Okay. So here are some more examples. We discussed quantum wells when we discussed semiconductor devices, and this is a different version of a quantum well. The quantum well I described to you was a well, potential well, which is a square, where we had, for example, 3 different semiconductors, gallium arsenide and aluminum arsenide, have different band gaps, And the gallium arsenide has a smaller band gap than aluminum arsenide, so then it creates this potential well, and you can have some bound states in that potential well. And those are similar to graphene, right? Because if the layer of gallium arsenide, the middle layer, is thin enough, then the wave function takes the entire space between the layers, and then in this sense it's also two-dimensional, just like graphene. Here are a couple different versions of a two-dimensional electron gas, a quantum well, now formed not by 3 semiconductors, but just by 2. And so here we have silicon dioxide junction with a doped silicon. And here we have similar semiconductors, gallium arsenide sandwiched with aluminum gallium arsenide. And what happens here is there is a peculiar band bending effect next to the interface. So here is a plot of the bottom of the conduction band, and here is the top of the valence band. And at the interface, due to some mismatch in the chemical properties of the two materials, some charge mismatch, for example, then the bands bend. And they form this triangular shaped confinement. And notice only in the conduction band this happens. So in the valence band, there isn't a place where holes can be confined. Right? So there is only this little notch in the conduction band. And for a certain potential applied from the outside here to the metal outside of the structure, you can have the Fermi level, which is a dashed line here, above the bottom of this triangular triangular notch. And then that means you're going to have some electrons living here. And so this is a metal oxide semiconductor structure, MOS. So that's what's also the foundation of MOSFETs. Right? The same technology can be used to create these two-dimensional electron gas layers, right? Because now we're looking in cross-section, but if I were to stand here and look at it, I'm going to have a two-dimensional plane of electrons in front of me. And those electrons will be so tightly confined that the wave function here, the wave function size given by the inverse Fermi velocity, or the Fermi wavelength, will be of the order larger than this notch here, of the same order. So then, in this sense, it is a two-dimensional layer. So only one of these kind of wave functions will be occupied there. And it's a similar story with gallium arsenide. There is also this triangular confinement. In the case of MOS devices, we need to use a potential on this metal to pull the bands down. In this case, people came up with a nice trick where they put some charges here, so some distance away from the boundary, these silicon charges, and you can imagine these positive charges attract negative charges in the notch in the triangular well and induce this two-dimensional electron gas. This has advantages because you just have those electrons there. You don't have to do anything. Here you have to apply voltage to adjust the chemical potential to create this 2-deg. Okay. This also is a nice trick because these kind of dopants are moved away from the channel, from this triangular position, and so they don't create as much disorder. Right? These donors, dopants, and semiconductors cause disorder, and this allows to grow a pristine interface, and then this disorder is somewhere else, not where electrons live. And what that allowed us to gain is enormous mobilities. Right? So if at low temperatures these gallium arsenide structures reach mobilities in the millions or tens of millions in these units of volt centimeter squared second. So these are the units of mobility. You can convert it into something that makes sense to you. I can tell you what it means in terms of the mean free path. Right? Mean free path is the distance that electrons can travel before they scatter. So this gives mean free paths of microns, tens of microns, hundreds of microns. So fractions of a millimeter electron can travel before it scatters, and that's remarkable. So that leads to the observation of new physics that we're going to discuss in the second half of the lecture today. Right? So you can think of this two-dimensional electron gas as really a free electron gas in the sense that defects in the crystal, defects in the lattice don't matter much. They are out of the equation. It is such a clean system. Bouncing off electrons off of each other, interactions of electrons can play a role, but bouncing off of some scattering sites, some impurities, is out of the picture. So very, very clean and low-dimensional system, right? Not something that nature gives us, but something that careful engineering allowed us to create. Okay, let's start with some basics, understanding some of the sort of first order differences that 3D and 2D has. And the first difference is in what the density of states looks like. Okay, density of states you already should have gotten from this course. So that's an important number in various things. And we start with recapping how we calculate the density of states in 3D. Right? In 3D, free electron gas, right, Fermi gas, we have a Fermi surface, which is a sphere. Right? When we don't have a lattice, then the Fermi surface is a sphere. And so all the states inside the sphere are filled and the states outside are empty. And we want to count how many states there are per volume of that sphere or at a certain energy. Right? What's the density of states at a certain energy? So how do we derive this? Well, remember that we are in 3D, so volume is dkx times dky times dkz. And the volume of a single state would be that divided by 2 pi to the third power. Now this factor of 2 here comes from spin degeneracy. So this is the formula. It's going to have 4 pi over 3 there as a prefactor. Now, if you want to get rid of these vectors here in this formula, right? You can go from integrating in 3 dimensions and figuring out the density at some random point in k space to figuring out what is the density of states for a vector k of magnitude k of length k. Doesn't matter which way it points, right? There is a symmetry, and so then you convert from dk vector to 4 pi k squared times dk, right? The surface area of a radius k times dk, right? So it's all simple stuff. You plug it in here instead of dk, and you get this for the density of states, still in terms of k. But what is more useful, right, is to know what is the density of states in terms of energy. So we have to go from k to energy. This is stuff that I've gone through with you before, right? So this should be familiar. From kinetic energy formula, essentially, we can extract k squared and plug it in to the formula for the density of states. Simple math. By the end of the day, gives us this expression, right? So we start in three-dimensional space, and we get this expression. So it has some pi prefactors. It has a mass of a particle, could be a free electron, could be an effective mass. And it has this square root E dependence. Now, what do you think changes when we go to 2D? Would it be the prefactor, the mass, the energy, power? Yeah, that's a good intuition, right? Because we had this expression where we went from decay to integrating over a sphere. So there will be some different expression here for what decay means in 2D. That's right. Okay, so just for your visual record, this is what the density of states looks like in 3D. It's a bit not the best picture. I can draw over it to make it nicer. Provided my drawing skills are better than the pixelation here. But it's basically the square root function. So starting from the bottom of the band, bottom of the conduction band, for example, in a 3D crystal, we're going to have not so many states at the bottom of the band, and then the density of states will grow as we move away from the bottom of the band. Why is that? Because we are going to a larger and larger Fermi sphere, and so states on that Fermi sphere increase in number as we go out. So this makes sense, right? Larger Fermi sphere, more states, larger density of states. Okay, let's do the same derivation for 2D. We expect a different power, right? Okay, so eigenstates of electrons in a free electron gas in 2D, same math as in 3D, except we just have two components here, kx squared, ky squared. When we try to calculate dk vector, we don't get 4 pi r here, 4 pi k, we get 4 pi k squared, we get 2 pi k. That's the length of the circle. So now Fermi surface is actually a circle. It's a Fermi circle in the space of kx and ky. It's a Fermi circle. There is no third dimension anymore in this problem. It's quenched, right? In a practical system, there is a fixed kz. But in math, we can just pretend it doesn't exist, the third dimension. Okay, so then there is, of course, also a different prefactor, not 2 pi to the third power, but 2 pi to the second power. That's the volume of one single state, is dk divided by 2 pi to the second power now, right? These 2 pi's come from conversion from real space to reciprocal space. Right? That's where they come from. And the factor of 2 from spin degeneracy. And so the density of states can be represented like this in 2D. And if you plug in the expression from here, you're going to get this formula. And in this formula, energy cancels out. So this k here gives you square root e, and this dk de gives you another square root e, so it's gone. It's a pretty bizarre result, right? So the density of states in 2D is a constant. It is independent of what your energy is. Density of states in 2D is a constant. So since we're on it, we can also do this for 1D, but first let me show you the graph. Okay, it's not much to this graph. Constant, it's a constant. Okay, depends on the mass. Depends on how band opens up. That's it. Constant. Okay, so there is a big difference between 3D and 2D, obviously. Now let's look at 1D, and it's going to come in handy next time. Okay, so states in 1D, that's just a parabola, one-dimensional dispersion relation, kx, e, there's a parabola, that's the bottom of the band. If the Fermi level is here, then the Fermi surface is just 2 points. That's it. There's just 2 points. It's not a circle, it's not a sphere, it's 2 points. That's the Fermi surface. Okay, so we repeat the same calculation. How many states at a given energy in this case? So we need to figure out what dk is. Well, dk is just dk. Dk vector is just dkx. So we plug it in. There is a single 2 pi, because we're in 1 dimension. And there is a factor of 2, so there's 1 over pi. And the density of states just has dk'd by dE, which is 1 over square root. So to go from k variables on the left to e variables on the right, we have to do this transformation here, right? Easy. So we have dk by dE. dk by dE from this formula is 1 divided by the square root of E. So the density of states in 1D is 1 divided by the square root of E. We had square root of E in 3D. We had a constant in 2D. And we have 1 over square root of E in 1D. So it seems this function grows as we lower energy. So there are more states at the bottom of the band than there are at the, in the middle of the band. So here is the function, which is 1 over square root of E. Here's the bottom of the band, E equals 0. There is actually a divergence. So this was first calculated by a physicist named Van Hove. So this divergence is called Van Hove singularity. Singularity. So coming back to Hawking, right? The singularities, black holes, there you have it. In 1D, electrons are piling up at 0 energy. All right. So we need to introduce one more concept when we talk about real systems. So that was purely 1D, purely 2D, forgetting about the real nature of how we get these systems. Right? So the real nature of that is that we confine some wave function, like we squeeze it into a single orbital of graphene, or we confine it in between two semiconductors in a quantum well, like is shown here. So here is a quantum well of length L. So this could be our gallium arsenide, and outside it could be aluminum arsenide. And in between we have a quantum well for which we can solve a particle in a box problem in this direction. And in general, we might have more than one eigenstate here, more than one solution to the Schrödinger equation in this confining direction, which is called the y direction here, I believe. So it's ky. And then originating at each of these solutions, there will be its own spectrum of two-dimensional solutions. What do I mean? I mean that always we actually live in a three-dimensional world. So we need to worry about x, y, and z. But now one of these, let's say ky in this case, is fixed. It can be k0, k1, k2, k3. It can only belong to a discrete set of numbers. I don't like it to be ky. Let's make it kz, right? And then xy will be free, unconfined. So let's make it kz. So let's say kz is equal to k1 is this wave function, and kz equal to k0 is this wave function, and this, ignore this one. So then this part here can be k0 squared or k1 squared, something fixed. And each family of these, so let's fix it at k0, then we can define a family of eigenstates with different kx and ky as belonging to a subband, which would be the zero subband. Okay? You following me here? Right. So the direction in which we can find along this quantum well growth direction, that's the z direction, and for a fixed eigenvalue of in kz, we have unconstrained kx and ky. So we have a two-dimensional electron gas that belongs to the zero subband, and then we could in principle have another one. We could have another two-dimensional electron gas belonging to the first subband. Now, you could have both of these subbands occupied if you have enough electrons. You may have not enough electrons, and then they all fit in the bottom subband. But then if you have too many electrons, then they will start occupying the second subband, maybe even the third, depending on how many you can confine here. Because none of these potentials are infinite potential wells. They are some finite depth. So they might confine 1, 2 subbands, and then if you put even more electrons, those will not be confined anymore. They will be 3D particles. Okay, is this clear? Okay. So you can have subbands in these systems. So how does it look in 1D? So this is a situation where you have, let's say, a cylinder, could be a nanotube, nanowire, cylinder, and its ky and kx directions are confined. You have two directions confined, and then you have infinite z. Let's say this nanowire has infinite length, right? So then you can have the following band structure. You can have, as a function of this kz, parabolas offset by a fixed value of kx squared plus ky squared. Now two dimensions are confined, one is free. So we have parabolas offset. Now at the onset of each parabola, you're going to have a Van Hove singularity in a density of states. Because for each one of these, you're going to have a density of states which is proportional to 1 over square root of E minus En, where En is the nth energy of the subband. Right? The way I written down this function only makes sense for E greater than En. So this is how it would look with one-dimensional subbands. Here are two-dimensional subbands. So what does this mean? This is the situation of a quantum well. So one dimension is constrained, one dimension is confined. Let's say the z direction is confined, and x and y are free. So now as a function of some x or y, you have parabolas. But then they're offset by some values of kz squared, right? So kz squared equal 1, 2, 3, 4, and you have the squares of the numbers here. And each subband brings in a constant density of states. But then when you have two subbands, you have double the constant. When you have three subbands, you have triple the constant. And so you are making this kind of function, density of states as a function of energy in the presence of the subband. So if you can occupy these four subbands, then the density of states will be this kind of a step function, because each subband will give you equal constant. And interestingly, this dashed line, this envelope, is the 3D density of states. So the farther we go, the more subbands we occupy, the closer it merges with the 3D.
Yeah, where the energy gaps between different states increase?
So it's because you have the energy of h bar squared over 2m kx plus ky squared. Those give you the parabola. And then the offset here is the quantized value in the third dimension, which is kz squared. And these k's go 1, 2, 3, 4. So energies go 1, 4, 9, 16. Okay. And the density of states is the same in each subband. So these are equal height steps that we have here. Okay, so this is another look at the same thing, 2D. Let's say we have two subbands confined in a potential well in the z direction. X and y are free. So at each energy of confinement in z, E0, E1, we have a parabola originating in the kx, ky space, and the density of states is a step function. There are no states below E naught. And then above E naught, there is a step, and then above E1, there is another step. By the way, if we're talking about just a free band in 3D, then the states would start here, right? So the density of states in 3D starts from 0 energy here. So effectively, by confining in one of the dimensions, we empty some region of the energy space, and we make the band gap a little bit larger by this confinement energy. So confinement can be used to increase the band gap by the confinement energy. So if you look at this system, then the gap in this system will be the 3D gap plus E naught, the confinement energy. Okay, this is the summary of all possible low-dimensional things that can happen. So let's look at the blue one first. That's the one we already know from almost the entire semester. Density of states in 3D. This is the square root of E function. And then density of states in 2D is a constant as long as you have one subband. But if you have multiple subbands, then it is a sequence of steps. Then in 3D, in 1D, you have these Van Hove singularities. And they correspond to the beginning of each one-dimensional subband. And this plot also shows you what happens in 0D. So if you imagine confining your system in all 3 dimensions, then you're just back to the simple particle in a box problem. It's a 3-dimensional box, and it is just going to have discrete energy states, right? Like we know from quantum mechanics. And those are the black lines here. Those systems are called quantum dots, or 0-dimensional systems, where the wave function is the same size as the system. So for a semiconductor, it could be tens of nanometers, or it could be the size of one atom. Okay, so this is peculiar, right? A little unexpected, although very simple math. It sets us nicely in the further discussion of 2-dimensional stuff. Now I'm going to show you something that is truly remarkable and much more unexpected, unless you've already seen it before, of course. It's what happens to the Hall effect when we introduce quantum mechanics, right? So, okay, this is a recap from the beginning of the semester to remind you what I mean by Hall effect. Hall effect is this transverse voltage, right? So it originates from just simple Lorentz force trying to push carriers in a slab in one of the directions. And you can imagine this works especially nicely in a purely 2-dimensional system where the thickness of the layer is 0 and there is nowhere to go in the 3rd dimension. You can only go left or right or straight. So the Hall effect manifests itself remarkably well. And the way we derive Hall effect is just by writing down the equation of motion from the Drude theory. So we add the Lorentz force on the electric force, and we have this Drude term, which is the includes the scattering time. Remember this? So there's a scattering time after which electrons randomize their momentum. Actually, in Drude theory, we assume that momentum goes to 0 after a scattering time t, and then the particle has to accelerate all over again. And when we were talking about this theory, we had in mind that this time is pretty short, and that scattering happens all the time. Electrons just barely fly and then scatter, and then they have to accelerate again, and this happens on a very, very short distance. And now I told you that in these 2DEGs, in these semiconductor structures, they can fly for microns and microns, which means millions, if not tens of hundreds of millions of lattice sites without any scattering. So this time becomes very short. All right, but what is the consequence of this? Well, because there is this cross product, right, V cross B, then conductivity becomes a tensor. Like cross product, you have vectors crossing, and conductivity or resistivity is a tensor. You can still write Ohm's law, but it's a tensor. And basically, you have off-diagonal elements in this tensor. So whereas diagonal elements just give you the simple Drude theory result for conductivity or resistivity, which just tells you that if you try to push current in this direction, there will be a voltage developed in that same direction. But with this magnetic field on, if you try to push electrons this way, there will be a voltage developed across. So there will be this whole voltage transverse to the flow of current. Okay. And how does this look? Well, it is a fairly simple graph. As a function of magnetic field, resistivity rho xy, which is these terms, of diagonal resistivity, which means you pass a current in the x direction and you measure voltage in the y direction. It just grows with magnetic field, like this. So it's just proportional to the magnetic field. So you got a whole voltage, which also depends on magnetic field. For a fixed current, it will just simply grow. Okay. And so then people got a hold of one of these two-dimensional electron gases and decided to measure it in magnetic field, also at low temperatures, so that quantum mechanics effects manifest themselves nicely, and we really can talk about two-dimensional electron gas. And they found these kind of curves. Right? So this is very far from a straight line. So you can say, wow. Right? It's okay, you can say. All right, so actually down here, at small fields, it does look like a straight line, right? So this is sort of a close to classical behavior down here. This looks like a straight line, and then it starts to wiggle, and then it creates these dramatic steps. And these steps seem to grow, become bigger steps as we go to higher fields. But if you look at these steps from a slightly different perspective, they are actually equal size. So this is plotting resistivity, but if you plot conductivity, then each step is E squared over h in conductivity. And they are all the same size, E squared over h. So if you plot in resistivity, then they look like this dramatically increasing staircase. Okay, so this is called the integer quantum Hall effect, to distinguish it from fractional quantum Hall effect, which we're going to try to touch upon just very briefly at the end of the lecture, which is an even more bizarre phenomenon. But let's set a goal of understanding this effect. This is uniquely 2D, very interesting and unexpected effect. Okay, so we have these dramatic steps in Hall voltage, which is across the sample, right? You pass a current this way, you measure voltage like this, it has these steps. But also something very bizarre happens to the longitudinal voltage, which is rho xx. So this is rho xy, but the green curve is rho xx. So what you expect to happen to rho xx is not much, because some electrons get diverted to the left, some get diverted to the right, that they still have to flow all in the same direction. And this is what kind of happens down here, not much, and then it starts to oscillate until it has this dramatic behavior. Whenever we are in the middle of the step, there is actually no resistance in this direction. It looks like a superconductor. And then there is a spike when you go through a step. So actually it is in between these. So it looks like there is a sequence of transitions between being looks like a superconductor from this plot and being a conductor. So that is also the behavior of rho xx is very strange. In fact, we will see that even though it shows 0 here, there is actually no current flowing. So there is actually an insulator there. All right. So let's try to understand it. To understand it, we need to go back to cyclotron motion. And this is highly justified here because I told you that electrons can fly without hitting any obstacles in these materials. And so you can actually make a pretty large circle inside this 2-deg and not experience any scattering. So once you apply magnetic field, especially a sizable one, all electrons start doing this cyclotron motion. The entire two-dimensional electron gas are doing this. And what do we know about this motion? Well, it is just happening under the influence of the Lorentz force. And this happens from a very simple derivation that it's a centripetal force with this cyclotron frequency, which is dependent on magnetic field. So the higher the magnetic field, the faster they go, like this. So this is a classical picture. What happens in quantum? These orbits, this cyclotron motion becomes quantized. And the argument for it being quantized is the same as for many other things we discussed. It's because the electron is a wave, and only that orbit will have some kind of a finite probability of being observed, the one that includes an integer number of wavelengths. Okay. So basically it means that there can only be a discrete set of radii for these orbitals and discrete set of frequencies of this motion. And it turns out that you can map the problem of quantum mechanical motion in a magnetic field, the cyclotron motion, onto a simple harmonic oscillator problem. And then the spectrum is just the same as for the simple harmonic oscillator. So for a given magnetic field, for a given cyclotron frequency here, you're going to have these kind of eigenstates which are equidistant in energy for these electrons. Okay. I'm going to show you in a moment how that comes about, but let's first think about it for a second. So from a classical point of view, it means that the orbits are quantized with this kind of radii. It's a sequence of radii which go as square root of n. The area grows linearly. And you can define some kind of a characteristic magnetic length which is related to the cyclotron orbit. That's the classical radius of cyclotron motion, which will be denoted LB here. Okay. So these things are called Landau levels, and turns out that they are responsible for this integer quantum Hall effect. So how do you solve quantum mechanically this problem? You use this thing I already showed you before, how you include magnetic field in quantum mechanics. And now I remember how it's called. It's called canonical momentum. So you use this canonical momentum formula that I already used for you. And then for the vector potential, you can use this very simple gauge where magnetic field is just perpendicular in the z direction, and that means that you can say that vector potential is just b times y, so it's just dependent on the y. You can use another gauge, and also there is some gauge uncertainty in this definition of A, but with this gauge you can show that the Hamiltonian becomes very similar to, actually identical to a harmonic oscillator, because there is this y squared term which looks like a parabolic confinement for some kind of a particle. And so then once you realize that, you can solve everything else about these Landau levels. you can write down their wave function, their spectrum, and is directly mapped to a simple harmonic oscillator motion. So because we have many electrons and they all move in these cyclotron orbits, then each of these Landau energy levels can have multiple electrons in it, because an electron on the left side of the sample can be in the lowest eigenstate. An electron on the right side of the sample can have the same energy, because their wave functions don't overlap. And so Pauli exclusion principle is perfectly satisfied. So they can have exactly the same energy because they are in different parts of the system. Right? So then each Landau level can have this enormous occupancy. It's almost like you have bosons. Except the difference with bosons is that each electron does take up some area in the 2-deg, and they cannot infringe on each other. Okay? So the difference between a classical picture and a quantum picture is that in a classical picture, we just have these single cyclotron orbit value for each magnetic field. In quantum mechanics, we have now this harmonic oscillator spectrum. So you can be in the first Landau level, second Landau level, third Landau level, and each of them comes with its own wave function, which are shown here. They are very similar to the simple harmonic oscillator wave functions. So if you look radially in each Landau level, it is like a simple harmonic oscillator. Okay, so what is the consequence of this massive degeneracy? It is shown here. Here at zero magnetic field, we have this density of states in 2D, which is a constant, which means that at any energy, for any value of energy, there is the same density of states. There is the same number of levels in an energy interval, no matter where you are. Okay? And now we impose a magnetic field perpendicular to this system, and by this, we confine all electrons to this very discrete set of Landau levels. And so at finite field here, we just have the first Landau level, the second Landau level, and so on. Let's say our Fermi level is here. So all of these are filled states. And now we only have these two possibilities. What happens is all of these electrons have this energy of the first Landau level, and all of these electrons have the energy of the second Landau level. They all collapse into this one level. And so each level then has an enormous, enormous degeneracy. And once again, that's because electrons were free to move everywhere, so they formed this Fermi surface before. And now each one of them is confined to a small puddle, just rotates around magnetic field. And so they can have, many of them can have the same energy, which is given by the Landau spectrum. And then there can be a lot of them at that energy because they don't overlap. The Pauli exclusion principle is satisfied. So you can see that the density of states now is something like 1 over the area of one level. There is a spin degeneracy already included here. This is for the integrated density of states for the entire Landau level. But then the full formula of density of states will have these delta functions. So the density of states, rather than being a constant, becomes a sequence of delta functions at the values of the Landau levels. And this is the cartoon for it. Left-hand side, you have zero magnetic field. You have a well-defined Fermi level at zero temperature. All the states below are filled. Now, At finite field, you only have these delta functions, these Landau levels available to you. You cannot be anywhere else. And these are shown with some finite width, and that's if you include some amount of disorder. Right? So if there is a perfect sample, then all cyclotron orbits are exactly the same, and these are delta functions. If the conditions in different parts of the sample are slightly different, there could be a slightly different radii, and then there is a width to it. And this also shows you until how pure has to be the system to observe it. So when they start to overlap, then you will just be back to the zero field situation. Right? Okay, so now interesting thing can happen. We increase magnetic field going from A to B to C. And then what happens is we increase the cyclotron frequency. Cyclotron frequency omega C is proportional to the external field. So we increase the cyclotron frequency, means we increase the spacing between these delta functions. We increase the energy level difference between Landau levels. And what happens then is that for certain values of B, we are passing through a Landau level. And that means we have sort of a half-filled or partially filled Landau level. And for most values of B, we are in between Landau levels. So when we're in between Landau levels, like in the case A, for example, what does this remind you of? There are fully filled Landau levels and then partially empty, kind of like an insulator, right? So in between, it's like an insulator. And then when the Landau level is partially filled, this reminds you of a conductor, like a metal. So you have some, you can imagine in principle electron orbiting here and then hopping over and orbiting over here for a while and then hopping to the next position and kind of moving through, right? You can imagine that this could happen, right? And if they are all doing this and all the spots around are filled, there is nowhere for an electron to go. The entire Landau level is filled, and there isn't a wave function nearby to hop onto. So then you have an insulator. So this is how we start getting the intuition for those oscillations in resistivity. And this is indeed the explanation. So here is the magnetic field axis. X-axis is the magnetic field, and the black lines is the fan, is Landau fan, is how Landau level energies change with magnetic field. So at any fixed magnetic field like here, the positions of these mark the positions of the Landau level energies, and here is the Fermi level. So as these levels pass through the Fermi level, you can see what happens. This sawtooth pattern happens. So most of the time, all the field states are below the Fermi level, and then when one of the Landau levels passes through the Fermi level, we are in a situation where there are some available states. The density of states is a delta function, set of delta functions, but only when the level passes through the Fermi level we have some states available, and then the level, this level goes above the Fermi level, and so all the states there are filled, and we start filling the next level. So it looks like a sequence of metal to insulator transitions as we change magnetic field. And this is what's responsible for this effect called Shubnikov-de Haas effect, which is oscillations in conductivity as a function of magnetic field. So both rho xx and rho xy show these kind of oscillations. This is a very nice effect. You can see it's a quantum effect, so you have to cool down to see a large contrast of these oscillations. And from these oscillations, you can learn a lot about the system. You can learn the density of states, the density of electrons, the effective mass, the number of occupied subbands, and so on. So what's the origin of these oscillations? Each oscillation corresponds to a Fermi level pierced by a Landau level. And so you have a high density of Landau levels at low magnetic fields because the omega c is small. And then the density of Landau levels drops as omega c grows. It happens less and less frequent. And so the periodicity of these oscillations slows down in magnetic field. But actually, if you plot it in 1 over b, it's equidistant. So all the oscillations become equidistant if you plot it in 1 divided by b on this axis. And that's also how you know that these are Shubnikov-de Haas oscillations. So this is a very popular technique for characterizing two-dimensional systems. For example, okay, I do not know precisely where this graph originates from, but I can see that it looks like a single period here, but as we increase the frequency, we start resolving some sub-harmonics in these oscillations. And this could indicate that multiple subbands are occupied in the 2-deg at zero field. So each subband would have its own Fermi velocity, and that would lead to different periodicity of oscillations, for example. This is one example of something you can learn from these things. And where are these oscillations happening? They're happening here in this curve at low magnetic field. These are these green oscillations, for example. And the red curve also has some wiggling around the straight line, which corresponds to Shubnikov-de Haas oscillations. So we have explained these oscillations. And so as the density of Landau levels drops, you can see that these oscillations become farther and farther spaced out. And you can see that these dramatic steps and these dramatic peaks in conductivity out here in the integer quantum Hall regime have the same origin, right? It just continuously goes from oscillating a little bit to just becoming this. It's the same phenomenon. It's just that they become farther apart, and rather than oscillating, they go through deep valleys and sharp peaks. And so indeed, these steps and these peaks correspond to transitions between just a few Landau levels in the system. So this last one, for example, is where you have just one Landau level. So magnetic field is so large, omega c is so large, that all electrons in this 2-deg fit into a single Landau level. And if you back away, reduce the field a little bit, you can be in a situation where there are 2 Landau levels occupied. The omega c drops, and all electrons in the 2-deg are divided into 2 Landau levels. Okay, so now let's explain these steps and these sharp peaks. So I can explain it quantum mechanically and classically. So I always prefer to start with classical, as it gives better pictures, although it's completely wrong. So for classical, we need to invoke these skipping orbits concept. So remember, we have a very clean system, not much disorder. And so electrons in this 2-dimensional layer are undergoing some kind of a cyclotron motion. But now each real sample has some edges, right? And here let's introduce the upper edge and the lower edge. And let's imagine that we find an electron somewhere pretty close to the edge here, moving with some velocity. It might run into the edge, and then it will scatter, and then it will scatter again, and it will just bounce off of the edge under the influence of the Lorentz force, and it will kind of travel along the edge in this skipping orbit trajectory. So this is classically called the skipping orbit trajectory. And now imagine you increasing the magnetic field and lowering the temperature, and this electron becomes a wave function. Becomes this blurred wave packet. And classically it's confined to this region, but quantum mechanically it takes up this entire region. The wave function takes up the entire region. And so now what you've done is you've transitioned from two-dimensional electron to an electron confined to the one-dimensional edge. In the presence of magnetic field, you create these one-dimensional edge channels where electrons can exist. This is what happens. There is some protection against impurities. So if this edge is not perfect, let's say there is an impurity here, then it does a skipping orbit, hits an impurity, but then Lorentz force will make it go around the impurity a few times until it scatters again and continues on the edge. So this is a very robust effect where backscattering is impossible. So this is not simply a one-dimensional channel. It is a channel where you can only move one way. You can move this way, but you cannot move back, because magnetic field forces you to skip always in the same direction, so long as you don't change your charge, which does not happen in these systems. So this is a one-dimensional, one-way street on the edge of a two-dimensional system. So the word for it is chiral. And these are known as chiral edge channels. Chiral means going one way in this case. Now, interestingly, let's look at the other edge of the sample. Here, we have the same direction of magnetic field, the same charge. Here, skipping orbit goes like this. And so whereas here we can only move right, here we can only move left. So these chiral edge channels come in pairs. It depends on whether you're on one side of the sample or on the other. So the geometry of the sample determines how you go. If you're an electron stuck in one of these edges. Okay? So this is a semi-classical picture of edge channels. And this is a quantum mechanical picture. So it is a finite width two-dimensional system, right? So now we have it confined in a third dimension, and it's also finite but largish width in 2D. So here is one edge, like this edge, and here is the other edge. And what we have in the middle is 10 Landau levels, equidistant in energy, Landau levels. And what we have near the edge is confinement potential rises because we are leaving the semiconductor, and the density of electrons drops. So you can imagine it as lifting the bottom of the band. And so you are going through, and if you have your Fermi level set somewhere here, doesn't matter where, all the energy levels are lifting up, and they are all going through the Fermi level at the edge. So in this case, you have 10 levels confined in one dimension on one side of the sample and 10 levels on the other side of the sample. If I drop the chemical potential down here, I'm going to have one level going forward and one level going backward on the other edge of the system. Okay, so one-dimensional chiral channels, because you're lifting the bottom of the potential, reducing the density towards the edge, they are piercing the Fermi level. Okay. So here I can explain to you half of the story of why there are steps in the Hall effect, and the other half will have to wait until next time because it has to do with one-dimensional systems. But let's consider this geometry where we can try to pass current from 1 to 3 and measure voltage across 1 and 3 or across 2 and 4, right? Local and non-local measurement, or transverse and longitudinal measurement. So this kind of a cross sample. And let's say we have 2 Landau levels here. So we have 2 edge channels circulating around the edges. And all the electrons here in the middle are bound. They are insulating. So they are bound to these orbits. They're sitting in Landau levels, and they're not helping us at all. Because we try to pass a current through, these trajectories are closed. They do not lead anywhere. But these skipping orbits on the edge, they can take us from A to B. Okay? So then, let's say we have a chemical potential mu1 here and a chemical potential mu3 here. And we try to see what the resistance is going to be. So here we have these 2 channels, and these electrons start here and they end up here. And then they can also come from here and end up here. It turns out that electrons traveling in this direction don't lose their energy. They just keep going. So electrons starting here with the energy mu1 will have this energy mu1 here, and will have this energy mu1 coming here. And now we have also electrons on the bottom edge, and those electrons will start with energy mu3, will have energy mu3 here, and will have energy mu3 here. So if we measure the potential difference between 1 and 3, we're going to have half of them with mu1, half of them with mu3 on both sides. And so longitudinal resistance will be 0. There will actually be a 0 potential drop between these two. This is kind of a bizarre thing. And now if we measure between 4 and 2, we're going to have the potential difference here be mu1 minus mu3. And then the thing I'm not going to derive for you today, but you have to believe me, is that the current in each of these channels is fixed. The conductance of each of these channels is E squared over H. So this you have to believe me. So given this, we're going to have some transverse voltage which is quantized because the conductance is always the same, and we will have 0. We will measure 0 this way. But it is kind of an insulator because in the bulk, all the electrons are bound to the Landau orbitals, and only these edge channels allow this conduction. Right. Okay. I see a lot of excitement about these concepts. Actually, these are very important for various topological research that is going on right now. Let me just scare you a little more before I let you go. So there is also something called fractional quantum Hall effect. And this is when people made even cleaner samples. And they found that instead of having this staircase of E squared over H plateaus, or H over E squared in resistivity, in rho xy, there were a lot of other additional plateaus. So here is a plot at large magnetic fields. And actually, this is the regime that people expected. And they expected this plateau to just go on and then go into 2, 3, and 4, and so on. And they saw the zoo of other plateaus, such as, for example, 1/3. So this is the rho xx, but this is the rho xy plateau at the value of 1/3 of H over E squared. So this is a result that I cannot explain to you in terms of these simple edge channels and Landau levels. Those predict numbers like 1, 2, 3, 4, and so on, 60, but not fractional numbers. Okay? So it turns out that this happens due to interactions of electrons. So in these very clean systems, and the density is fairly low, it's a semiconductor, much less dense than a metal. Only 1 in maybe 1,000,000 atoms contributes an electron, and so on. Interactions between electrons play a role. And we already saw that interactions can produce magnificent things, like in the Hubbard model, like ferromagnetism. And this is one more manifestation. And one interpretation for these fractions is that out of these interactions, particles with fractional charges are born. And then they carry fractional conductance. Okay. So here is some examples of quasi-particles that exist in these edge channels in fractional quantum Hall effect. So there are still edge channels. The bulk is still insulating. But the weird fractions at which conductance happens tells us that the particles that are traveling around are not just electrons. Okay? That's the logic here. And so some of the particles could be like this. It could be an electron plus 3 magnetic flux quanta. And this is one particle. Right? But this shouldn't be too obscure to you, because we know about Cooper pairs, for example, paired states of 2 electrons. So this is another quasi-particle born out of interactions in the presence of large magnetic fields, but still fairly difficult to think about them. And then they can actually be fermions or they can be bosons, depending on how many of these particles pair up. And then, when they're bosons, they can undergo Bose-Einstein condensation and so on. They can also exhibit fractional statistics, meaning some modification between Fermi and Bose statistics is possible for these particles. Okay, so I'm not going to derive this for you. Robert Laughlin, famous theorist, came up with this model, and he could explain all of these fractions with this simple model of coupling flux quanta to charges. He explained all of these fractions except one, which is 5/2. He could not explain that one. And you're going to have a whole lecture on this stuff later on. Okay? So this is like a detective series, right? You think you understand everything, and then there's one loose tail, and it drags in another chase and another wild story. So this is what the 5/2 fraction is for this quantum Hall effect. All right.